Turtle graphics for Java. This is for CS141. So before we talk about that, let's talk a little bit about computers as simulators. So this is a quote from, not sure how to say the last name, Seymour Papert, or Papert, not sure. I'm going to call him Seymour. Computer is the Proteus of machines. Its essence is its universality, its power to simulate. Because it can take on 1,000 forms and serve 1,000 functions, it can appeal to 1,000 tastes. And so this is a quote from his book Mindstorms, which is from the late 60s. If you're not familiar with the term Proteus, here's the information from Wikipedia. Computers as simulators is a really powerful idea. You can use computers to simulate all sorts of things. Computational biology, computational chemistry, simulating financial markets, simulating sporting events to get the perfect fantasy roster. I mean, there's all these different ways that computers can be used as simulators. This is actually a really, really powerful idea. And so Seymour's kind of tapping into this idea while at MIT in the 60s to try to think of a way to get kids to do some computing, but in a fun and very creative way. And so the goal, would like the kids to develop problem-solving skills, would like them to learn by constructing and fixing and debugging something, and we'd like them to learn because they're making mistakes and they're fixing them. So by harnessing the students' creative instincts, their desire to draw and to paint and to, build things, as kids so often do in elementary school, but making them able to do these things on the computer, the idea is the students will be doing thinking, they'll be doing problem solving, but they won't think of it that way. They'll think of it as more of kind of a creative art endeavor. And so, John Dooley and I were talking about this. We're both very familiar with Logo. I distinctly remember back in 5th grade, we did a lot of stuff with Logo, which is, the language that Seymour came up with in MIT in the late 60s, and this was fairly commonly available in a lot of elementary schools back in the 80s, I remember. This was like the thing that you learned if you were going to learn to do some stuff on the computer. It was one of the programs that everybody seemed to have available. And I guess it just sort of innately made sense to me because I did it when I was a little kid, that the idea of a turtle kind of cruising around, dragging a pen behind it, and drawing things made natural sense to me as a metaphor. Looking back at this now, the late 60s up through probably the late 80s, even into the early 90s, I don't know that students that didn't grow up with Logo, the idea of a turtle carrying a pen around really makes a lot of sense. So I guess I'm just going to chalk this up to, it was a very different time back then. And then just the obligatory image of a person riding a turtle around. This is kind of what we're going to be doing, is like telling this turtle to go forward and go backwards and turn in various ways. So first I want to demo some code and then break down kind of bit by bit what's happening in the different parts of the example code, and then I've got some review questions at the end to try to see if you can apply the stuff that you're going to be able to learn here. So we're going to start with testturtle1. So this is the code that we've got with testturtle1. Here's main. Here's what the code's going to look like. We'll talk about each of these lines in a bit, but first I'd like to go ahead and run this and show you what it's going to do. So there we go. The turtle started out. We drove the turtle around. The turtle's kind of, you can see as the turtle moves, it's drawing this little line behind it. And we end up with this really cool picture that was generated by this bit of code. So now let's kind of go through these lines of code and see what's actually going on here. So here's the code kind of pasted into the slides here, and I've gone ahead and numbered the lines, but then I don't really need to refer back to the line numbering, so it wasn't really strictly necessary to number the lines. The first thing to note is there's one slight difference in terms of where the brackets are located. If you notice here, the name of the class has a bracket on it, its own line, and then main has the opening bracket on its own line, whereas over here the opening brackets are at the end of the line. You can do it either way. It's correct. It's really just a stylistic preference, and there is debate on occasion that'll still fire up in different parts of the internet about where the correct place to put an open bracket is. I don't really care as long as the closing brackets are going on their own line and are indented to kind of show you where things are going. Where the opening brackets go, not really as worried about that. It's kind of an aesthetic choice. So the first thing to note, we've got our public class testturtle. This is your standard way of starting a class. This is the name of the program. It has to be a legal identifier. And then we've got our main method, public static void main. Again, you need to know that you need this stuff here. You need to know that you need main here. If you don't remember exactly what the format of these things is, go look at a previous program, go look at an example program, look at some slides, figure out what it is and make sure it gets in there. If your code doesn't work because this is wrong or because this is wrong, you should be able to fix it. That being said, there's not going to be an exam question that says, regurgitate out public static void main, blah-de-blah. That's not a particularly useful task because you could just look it up. But that being said, this stuff does need to be there, and you need to know that it needs to be there. This is the first really new thing that we're doing. We're creating a new world. The world is basically, when you go ahead and run this, so we run the program, and we know this up here is called world. This drawing area where the turtle's going to drive around and draw things, that's known as the world. So that's what we're creating here. And so whenever you create new instances of things in Java, you end up using what's called a constructor, and then you invoke the constructor. So this entire process is typically known as a constructor invocation. Some general notes about constructor invocations. You're going to have this keyword new, and then the class name, and then a list of the parameters. And so a little more information about this. New, this is what's called a keyword, or a reserved word. It's a word that already has a special meaning in Java, sort of like int or double or class or public or for, these special words that already have a specific meaning. So you couldn't name a variable new because new, the word itself, already has a special meaning in Java. It means, hey, I'm about to do a constructor. Now we've got the name of the class. You would just put whatever the class name is here. You wouldn't literally write class name. You'd replace it with world or turtle or whatever thing you're trying to create. Then you've got your open and closed parentheses. And then you've got however many parameters that particular constructor needs to have. There's a way to look up what parameters constructors are expecting in something called JavaDoc or the API, which we will see later in this video. And so one important note, you can have 0 or more parameters depending on what the constructor asks for. So there absolutely can be constructors that have 0 parameters, just as there can be methods in Java that have 0 parameters. So putting all of this together, we can see this new world part creates a new instance of world. You can also see that we're assigning it to its own variable. So here we're creating a variable called world of type world, and then we're assigning it the results of this constructor invocation. And so, don't I have this broken down into... Yeah, there we go. This one I don't have broken down? No, I guess I don't. Okay. Well, anyway, that's what we've done with creating a new world. Great. So the next line, what we're doing is we're doing another constructor invocation. You know this is a constructor invocation because it's got the keyword new here. But here we're creating a new turtle. We're passing it this instance of world we just created. We're assigning it to this variable. Let me go ahead and break this down into more detail. So, and I've got this nicely color-coded to make the process sort of a little easier to see what's going on. So we know this is a constructor invocation, and it turns out that to create a new turtle, you actually need to tell it what world it's in, because there could be multiple worlds, multiple little drawing windows that you could expect to put turtles into. And so we need to tell the turtle, hey, this is the particular world we would like you to be in. And so that's being passed in here as what's called a parameter. So we've got new turtle, the constructor invocation, and we've got to put the parameter in here. Now we're assigning that into this variable, which is of type turtle. We're going to go ahead and name the turtle Jamal. That's the name of the variable. So this is a variable declaration. and we're assigning it the results of this constructor invocation. I should note we're trying to pick new names for things. Looking back at some of my previous slides from other courses, including previous incarnations of this course, I always picked the name Bob and then eventually would do Alice. So I would name everything Bob and then a few things Alice. And it occurred to me, Bob is kind of a very stereotypically, white guy of English descent name. And I really don't want to present the impression that a lot of the media stereotypes about computing, that it's kind of dominated by these, brilliant white guys who were programming since they were born or something like that. I don't want to do things that kind of buy into that narrative, because that narrative's kind of stupid, and there's a lot of ways to kind of poke holes in that. And also because it's so widely reinforced by things like popular TV shows like The Big Bang Theory, or, I don't know, back in the 90s, the comic Dilbert was very popular, and it was really just populated by, white guys who may as well have been named Bob. And so I'm making a conscious effort this year to try to pick a more inclusive set of names to represent a little bit better the diversity that Knox College, in fact, has here right now. I'm trying not to look like I'm this relic from the 1990s if I can possibly help it. I'll probably fail at that, in which case you can go ahead and point out that I am, in fact, using lots of references from the 90s and things like that, and that's okay. It's fun to make fun of me for that. But the point is, darn it, we're trying really hard to create a more inclusive environment and not buy into a lot of the negative media stereotypes that are, in fact, out there. Anyway, so once we get this turtle created, we actually need to do things with the turtle by going ahead and drawing lines and turning the turtle around and things like that. So these are all done with a series of what are called method invocations: forward, turn, forward again. So to move the turtle around or to have the turtle turn, we're going to use these methods. A note about the turns are in degrees, and the value can be a double, and you need to use a negative number of degrees for a left turn. So by default, the number of degrees is going to be a right turn or a clockwise turn. If you want the turtle to make a counterclockwise or left turn, or anti-clockwise if you're from the UK, you need to use a negative value. And note that the value for turn can be a double. But remember, anywhere you're expecting a double in Java, you can always put an int, and Java will just promote that int to a double. So here I'm saying turn 90, I could just as well say turn 90.0. Here I'm saying turn negative 45, I could just as well say turn negative 45.0. They would mean the same thing. The forward method, by the way, this does have to be an int, and the reason for that, the unit here is actually just a number of pixels, and there's really no value in trying to have sub-pixel resolution on a monitor. You can't draw anything smaller than a pixel, so TurtleGraphics doesn't really support it. So a little bit more about what's going on with these method calls. Method calls, these are instance methods. There are also static methods, sometimes known as functions, which we will also see, but for now, all of the stuff with TurtleGraphics that we're doing, these are all instance methods. There's a standard way to do this. You take the name of the instance that you would like to invoke the method on, you have to do a dot, and then you do the name of the method and then whatever parameters the method needs. So we're saying, okay, I'd like to take this turtle Jamal, I'm going to invoke a method on it, the method's going to be forward, and the distance I'd like it to move forward is going to be 100. So that's the standard syntax for any method calls that you're going to make in Java. So let's get to a couple of review questions here. Go ahead over to Moodle, try this out. Will this work? Based on what we know, do we think that we could go ahead and sort of stick both of the constructors on one line, or is that not going to work? Try that out. Hopefully you came up with yes. This will in fact work fine. The reason for this is the turtle constructor expects as a parameter something of type world. So in the past, what we've actually given it has been a variable of type world that we previously constructed. But since all it expects here is something of type world, we can just stick in the constructor call for world to go ahead and create a world, and then that world will immediately get passed into this turtle constructor. So remember, anywhere you're expecting something of a particular type, you can put a variable of that type. You can also put a method or constructor that will return something of that type. And for things like ints, anywhere you're expecting an int, you can also put a mathematical or arithmetic expression that will produce an int. and then it'll just go ahead and evaluate the expression and come up with the int. Method calls are basically like that as well. It's essentially an expression. So that's what's happening here. We're going to say, okay, create a new world, and the result of that constructor invocation, that's going to get passed into Turtle. So try this out. What does this draw? Go ahead and pop on over to Moodle and try this out. Hopefully you came up with a square. Now, one thing to note here, we're turning negative 270 degrees, but that's actually the same as a 90-degree turn. So a 270-degree left turn is the same as a 90-degree right turn, because remember, there's 360 degrees in a circle. So if you subtract 270 away from sort of your 360, you end up with 90. Another way to think about this is, you know the old saying that 2 wrongs don't make a right, but 3 lefts do? Sort of a joke saying, you know, if you make a right-hand turn, that's the same as making 3 left-hand turns. So 1 90-degree right-hand turn is the same as 3 90-degree left-hand turns. So 2 wrongs don't make a right, but 3 lefts do. See, who says there's no humor in computing? Let's look at another program here, because when we're dealing with the world and drawing stuff, one really important question is to think, well, where is 0, 0, since we're going to be dealing with coordinates. So let's close Turtle 1. Let's look at Turtle 2. Turtle 2 is Carla. This is essentially exactly that code. It's already been compiled. I'm going to go ahead and run it. We'll see if this does in fact draw a square. Look at that, it does. So that's fantastic. Now, one thing I've done, there's actually another method. There's actually many more methods to Turtle Graphics, but there's one more method we haven't really seen, which I'd like to go ahead and show off. This is the move to method. So we're going to say, Carla, I'd like you to move to 0, 0. And so wherever the turtle is after finishing drawing this square, it'll move from there directly to 0, 0, drawing a line behind it. So this will show us where 0, 0 is. Bam! Look at that. That's a little bit weird. Finished drawing our circle. Finished drawing our square. And then we went straight up here to 0, 0. Well, 0, 0 turns out is in the top left. It's a little weird. Often with Cartesian coordinates, we think of 0, 0 being in the bottom left, and then this would be like, you know, quadrant 1. But in fact, in computing, these are what are typically called screen coordinates. 0, 0 is usually in the top left. This is kind of a weird historical quirk having to do with, I don't know, really, really old monitors that had a refresh rate, and it started refreshing from the top left. I mean, this would have been a long time ago, and for whatever reason, this convention in a lot of computing applications, not all, but a lot of computing applications, of putting 0, 0 in the top left, and then as the x-coordinate increases, we go this way. As the y-coordinate increases, we go this way. So we're always looking at positive x and y coordinates, but with 0, 0 up here. Another way to kind of think about this is the x-coordinate is not really an x-coordinate, it's really a column number. And the y-coordinate is not really a y-coordinate, it's really a row number. So we're in, you know, row 5, column 7, or something like that. This is a common way that people will kind of think about things to make it a little bit less confusing, that 0, 0 is in the top left and the y-coordinates get bigger as they go down, is to think about it rather than x, y as column, row. Okay, so that's a little bit about Test Turtle 2 and where 0, 0 is located. Hop over to Moodle and try this out. So suppose you want to draw a polygon with a variable number of sides. So we declare some number of sides. It's an integer. We don't know what it is. Let's assume it's at least 3. And then we're going to have this little loop here. We want to make a polygon of this many sides. Each side's going to be length 100. What do we put here? So try that out on Moodle. So hopefully you came up with 360.0 divided by sides. This is because, remember, the turn method expects a double. You can give it an int and it'll promote it to a double, but you can also just straight up give it a double. The 360.0, this is a double. If you divide a double by an int, it'll promote this int to a double, and the result out of this will be a double. Now, if we know that sides will be divisible by 360, evenly divisible, so it'll be 5 or it'll be, you know, well, what else, 6 or probably, does 8 go into 360? I'm not really sure. A 9 would work, but 7 definitely wouldn't work. So if we know it's going to be divisible by 360, you could do this one. But since we don't know what size is going to be, we just know that it'll be 3 or more, then we have to do this version, so that otherwise we'll sort of be off by a degree here and there, and the more sides we have that are off by a degree, we may end up with the polygon not fully being closed. The two ends might not end up actually meeting up. So suppose you want to draw a circle. So we've got our turtle Casey, and Casey's going to go ahead and draw a circle. So we've got how many sides do we want, and what is the length of each side going to be. So what should we put in the blank? Which of these pairs, or none of the above? So hopefully you came up with 360 and 1. 360 different sides, each of length 1, if every time we're turning 360 divided by the total number of sides, which in this case is in fact going to be 360, so the turns here will be basically 1 degree. This will get us a whole bunch of little length 1 units with a 1 degree turn after each one. It'll approximate a circle for us. You could put bigger values in here, right? You could say 360 with 100. This will draw like a much bigger circle, and 360, 360. This will draw an even bigger circle, but they're not really circles. They're going to look much more like polygons, just with really big edges and 360 sides. So by keeping the length down around 1, it's going to look a lot more like a circle, at least hopefully. So it turns out that TurtleGraphics has many other methods. We've already talked about turn, forward, and move to. There's also pen up and pen down. If you tell the turtle to do a pen up, wherever you move it to, it will no longer draw. And then if you do pen down again, it will start drawing again. We can also set the pen color using this new type color. And so these are really powerful things to be able to do. And so the TurtleGraphics methods, there's a full list of them available. This is often called an API. API stands for Application Programmer Interface. Here's a version of it that is at Ithaca College. Can put up a version at Knox. The documentation actually comes with the TurtleGraphics package. I'm going to go ahead and click this and fire this up, and I think I'll make the font size a little bigger. This format here, it's a standard format. It's called JavaDoc, short for Java Documentation. If you look at this, you'll see you've got a little bit of a description of the class. You've got what the constructors are, what the parameters to the constructors should be. Then you've got this big list of methods. Some of them we're not really sure what to do with. We have this drop method that takes something of type picture. We don't really know what a picture is yet. This is a type we've never seen before, so that's a method we wouldn't really be able to do much with. But these, forward that automatically goes forward 100 pixels, and forward that goes forward by a given number of pixels, we've seen that method. We know we could, where is it? There we go, pen down and pen up. We've seen those before. We know that there's a move to method. We've used this method before. And then there might be some other methods that are kind of that could be kind of useful for us. Here we go. Turn left and turn right. This is a 90-degree left turn and 90-degree right turn. Those are obviously the same as calling turn with 90 or negative 90 degrees, depending on whether it's a right or a left turn. There might be some other methods in here. Set pen width. This will allow us to draw much thicker lines. That's pretty useful. And then there's some, like set show info. I'm not really sure, why we would need to use that right now. We probably don't. But in general, any new class in Java that you get for a new package, or really anything that comes built in with Java, is going to have a page like this of what's called JavaDoc, telling you all about all the methods, what the methods do, what the constructors look like, so on and so forth. Okay, let's look at one more example just of setting pen colors, because there's one kind of important thing that I need to show you about this. So this is test turtle 3. You can see here's the code, and if I go ahead and compile and run this, you'll see, there we go, the turtle moved forward 100 spaces. If we look at Morgan, our turtle here, we created a new world, we created a new turtle, we set the pen color to red, and then we moved the turtle forward 100. So that's why we got that red line here, as opposed to before when the lines were, green or gray or something like that. And so we can specifically pick the pen color. Now there's one important thing about using colors, you'll note we have this import statement up at the top, import java.awt.color. AWT is usually pronounced AUT. It actually stands for Abstract Windowing Toolkit. It was the very early Java graphics library. So if you try to use colors, you have to import color, and then you can say like color.red in all caps. There's also color.blue, color.green, color.yellow, sort of all of the basic colors that you could name. These all exist. These are actually variables. These are what are called constants, or constant or global variables, and they're sort of affiliated with colors, so you can say, color.blue or color.green or something like that. You can also pick specific colors by choosing red, green, and blue values and kind of mixing things together, but for a lot of the kind of basic drawing, you don't really need to worry too much about that. Now with these import statements, if you leave this import statement out and try to compile the code, it'll say that it doesn't know what to do with color, it doesn't recognize it, or it can't find it. If that happens, you need to know to stick in the import statement. Again, you don't need to memorize the import statements, but if your code doesn't compile because you're missing the import statement, you should be able to fix it either by going and looking at the slides or looking at a previous example or an example from class or something like that to get the code fixed. You don't need to memorize it, but if it doesn't work because you don't have it, you need to know how to fix it, what resources you need to look at to fix it. Another note about import statements, these are a complete statement. It has to end with a semicolon, and they do need to go before we actually start, public class, test turtle, or whatever, before we start the actual name of the class, the name of the program. They have to go before that. And they can't go inside the comments. You might have comments here or comments here, but this statement can't be inside the comment or it'll be ignored. So that's just some notes about import statements. Good, that's all we've got on this. I think I'll do a separate lecture for this stuff on fractals. So thanks for listening.